Hello everyone, welcome to my channel. I am Chetna and this is my data world. In this video, I will be doing a quick breakdown of the era of 1-bit LLMs paper. So let's get started. So this is the paper and this highlighted part. So it says we introduce a 1-bit LLM variant called BitNet B1.58 in which every single parameter or weight of the LLM is ternary. That is, it takes values -1, 0, or 1. It matches the full precision transformer LLM with the same model size and training tokens in terms of both perplexity and end task performance while being significantly more cost effective in terms of latency, memory, throughput, energy consumption. So now let's break this down. The first thing is it is a 1-bit LLM variant. Now what are 1-bit LLMs? 1-bit LLMs are large language models where each weight or each parameter that needs to be trained occupies a memory of 1 bit. The values that each weight or parameter can take are either 0 or 1. This is in contrast with full precision or floating point weights, which are 32 or 16 bits. So, this helps reduce the memory required to store the models. And then it also talks about perplexity and performance. What is perplexity? Perplexity is a way to measure the amount of randomness in the next word predicted by an LLM. Higher the perplexity, more random the next word is going to be. So it is good to have a lower perplexity for a better performing model. The 1-bit LLMs are comparable in terms of perplexity with other models having full precision but the same model size. This is also true for end task performance. Let's look at the diagram below. It shows that in terms of performance, BitNet or the 1.58-bit LLMs are a Pareto improvement over transformers with full precision. If you look at it, the weight matrix contains only 1 minus 1 or 0. Just to illustrate this point further, it shows that the full precision 16-bit model requires multiplication and addition, which is what is common for large language models, whereas with the 1.5-bit LLMs, you have 1 minus 1 and 0. So, in a way, it is feature selection or weight selection. So, a lot of these parameters are eliminated when they have a 0 weight, and the others are just added. So this makes the calculations also very easy. So it also makes the models faster. We also see something called a Pareto improvement of bitnet over transformers with full precision weights. What this means in this context is that we look at dimensions such as performance, your memory, throughput, latency, energy consumption, and so on. You see that BitNet is performing significantly better than transformers over memory, over energy consumption, and latency, while not harming the performance measure. And that is what Pareto improvement means. It improves the main metric without harming the others. Now we come to the crux of this paper, and that is the quantization function. In this 1.58-bit version, the weights need to be constrained to -1, 0, and +1. For this, the abs mean quantization function is used, which first scales the entire weight matrix by the absolute average value of all the weights in the matrix and then rounds each of the values to the nearest integer among -1, 0, and +1. Additionally, if we assume that QB is the maximum value in that range of weights, quantization for activation functions is not done between 0 and QB, but between minus QB to plus QB. Now, let's look at some results. In terms of latency, you see that PitNet, which is the orange line, is significantly lower than Llama, which is the blue line. And you can see that the model size is comparable. And also, in terms of memory, again, BitNet is significantly less memory consuming than Llama for the same model size, anywhere from 2.93x to 7.16x smaller. So, this basically shows that with one bit LLMs or the bit nets, you are able to significantly save on latency, throughput, energy consumption, memory, etc., without sacrificing on performance. This is the major contribution of the one bit LLM model. And that's it for today. I hope you enjoyed this quick breakdown of the one bit LLM research paper. If you want me to break down more research papers, please let me know in the comments below. And I'll see you in the next video. Until then, ciao!